So let's see the question. Question 1 today. Two very small, two very small identical circular loops. Identical circular loops. Two very small identical circular loops. 1 and 2. You can think of like A and B. Okay. I'll put it up like A and B. That would be fine. A and B carrying equal currents I. Carrying equal currents I are placed vertically or placed vertically with respect to the plane of the paper, plane of paper, with respect to the plane of paper, with their geometrical axis, with their geometrical axis, geometrical axis perpendicular to each other, with their geometrical axis perpendicular to each other, as shown in the figure. Basically, I feel like this is an entrance examination level question, but still, I want to discuss. I have interest in discussing this, so I am doing that. The next one is that okay. So the find the magnitude. I have not drawn the figure, so while solving the problem, I'll draw the figure. Magnitude and direction of net magnetic field. Magnetic field. Net magnetic field produced at the point O. Produced at point O. Okay. So this is the question which is given. So please note after that you can and I want you to watch the earlier videos in order to understand this one. So that would be better if you watch and then you try to correlate. Anyway, this record will also go there into YouTube. No issues on that. So the thing is, two very small identical circular loops A and B are carrying equal currents I or placed vertically with respect. I'll show you once you finish the writing. I'll show you how the arrangement is about. How the arrangement is about. Once finished, please let me know. Is that tricky question? This is like I tell you, this is like the level of JE or the you can think of a NEET level question or a JE level question or an MSET level question. This kind of questions are very much possible in that kind of examinations, and it can be for your board also. It's possible. So very interested in this question, so I want to solve it. So it's like it covers entire concepts together. Whatever the concept have to be covered for the circular loops, the entire concept is covered for you. Okay, so that will be done through this. Entire concept is covered. So once finished, please let me know.
Noted, sir.
Okay, good, good. Now let me show you the figure how it comes in. This is my coil A is kept like this, and the coil B is kept like this. This is the figure. Coil A and coil B. From the center of the coil A, so this is the coil A. It has a radius of R, let us say, and this is also a radius of R, and we have a point O. So we'll draw that. So it looks a little bit awkward. Okay. So this is the center of the second coil. Hope you understand. This is the B. So let us say the B is the center of this coil and A is the center of this coil. Okay. And this is my point O. At this point, you have to find the magnetic field. Now, both this from the center of the coil, BO and AO are of the same distance, that is X. This is what they have given. That is at a distance of X. Okay. The point O from the center of the coil is at a distance of X. The stuff is that what they have given is here the current direction. They have given the current direction. This is the current direction here, and the current direction here in this coil. They have given the direction of the current. Now, based upon this, you have to find the direction of the magnetic field. That's most important. And then they have, what else they have given is that it is these two are at an angle of 90 degrees with each other. So the geometric axis is at an angle of 90 degrees from each other. When you read the question, this you can understand. Now, stuff wise it's simple. So the what is the field at the point O is like, if you want to find the magnitude is mu naught, the number of turns in the coil you can assume n, and then I, and then the radius is r square whole divided by 2 into r square plus x square whole power 3 by 2. That's the formula at any point O, which is at a distance of x from the center of the coil. This is the magnetic field. Okay. Whether it is BA or BB, that's fine. At the point B, from the point B, it's the same. Value wise, it is same. Mu naught n I x square divided by, r square whole divided by 2 times r square plus x square whole power 3 by 2. This formula you have to remember. For the circular coil, this formula you have to remember. The magnitude of the magnetic field, either from it is BA or BB, it's same. For the coil B or the coil A, the magnitude wise they're same. But we got to find the direction of the magnetic field. So for that, what you had to do is you had to use the right hand thumb rule, what I told you. So here I told you about the rod. You had to place the thumb in the direction of the current, and then the curl of the fingers will come like this, and that gives you the direction of the magnetic field. I told you that. So here for the coil, if you do the same way, now you place your thumb in the direction of the magnetic field. Okay, thumb is placed like this. How your right hand fingers will turn? They turn to inside, right? This point I want you to get this, please. If you have not understood, please let me know about this. I'll repeat once again. Please let me know if you have not understood. Imagine a bangle first, as simple as that. You hold the bangle with your right hand such that the rim of the bangle, you keep your thumb to the rim of the bangle. Are you getting this point? Hello. You're not got, please let me know. So here I want you to hold a bangle in your right hand. If you have a bangle or any circular object in your right hand, you hold like this in your right hand and place your thumb on the rim of the bangle, and now your fingers will start turning into the bangle like this. Fingers will turn like this inside the bangle. Hope you got this easily. Fingers will start turning inside the bangle. Okay, this is how you hold the bangle if you had to keep like this, and this is the direction of current. That means your magnetic field is flowing inside like this, inside. So the direction of the magnetic field, it sucks from this point. Okay. Oh, yeah, that's the best word. It sucks from this point. So it's like it's entering inside. Okay, these field lines are entering inside. So that's how you get the field. And now look at here. You place again your right hand. Don't use your left hand. You will all go wrong. You have to use your right hand. And now place your right hand and then try to hold it. Your fingers will curl outwards. Okay. You place your right hand like this to the bottom B, put your thumb like this, and then fingers will come up. So it's like this. The magnetic field direction is like this. So to see the vector wise, they are 90 degrees like this, and your resultant vector is like this, B net. B net direction is like this. Okay. So the direction of B net we got, so it makes 45 degrees, of course. Why? The magnitudes are same, so it makes 45 degrees. Exactly, it bisects the angle. So it makes 45 degrees. That's the B net. So how do I find the B net? It's very simple. So you can see a right angle triangle here. So this is one thing. So how this right angle triangle will come? Okay, this is the first one. This is BA like this, and the BB part is like this. And now the resultant of the vectors is like this. The resultant vector is given by the parallelogram law. For to find the resultant vector, you draw a parallel vector to this one like this. This is my BB. Okay, this is the parallel vector, and this is leg, and the other leg, this is my hypotenuse. Hypotenuse is my resultant vector, B net. So the B net happens to be square root of BA square plus BB square. Magnitude wise both are same, right? Magnitude wise both are same. So B net happens to be B root 2. Just multiply this factor with root 2. That's all you have to do. So that is mu naught n I r square whole divided by 2 into r square plus x square whole power 3 by 2, and again multiplied by root 2, and this root 2 and this here you can give a root. So hence the answer. That's the answer you have, you need. So mu naught n I r square whole divided by root 2 times r square plus x square whole power 3 by 2. That's the answer for you. So very nice problem this is. Only thing is, how do you write the resultant vector is what you need. That's it. Is this clear, everyone? Once finished, please let me know.
Completed, sir.
Very good.
Sir, wait, sir, wait.
Yeah, okay.
Finished, sir.
Okay, right. Now we will do something called Ampere's circuital law. Ampere's circuit law. So I don't want to go with the definition first of all. It says that according to this law, line integral of the magnet. Now you may not be able to understand this. The line integral. It says that, okay. Anyway, I'll write the line integral of magnetic field. Magnetic field B around any closed path. Any closed path. Around any closed path in vacuum. In vacuum is mu naught times the net current, the net current the net current I net enclosed by the curve, enclosed by the curve, enclosed by the curve. And now it says that integral b bar dot dl bar. It will be confusing thing. I will explain. I will clarify all these things for you. Don't worry. Mu naught times I. That's what it says. So it's called a line integral. For now, don't worry about this line integral. This part. I'll explain that one by one. You will understand. I'll ensure that you will understand. This is Ampere's circuital law. So many people will get confused of this particular thing. There's Ampere's circuital law. It's there anyone is having trouble now? Okay, so everyone is in. Fine. Okay, fine. So what is this Ampere's circuital law? That's line integral of the magnetic field. Okay, definition wise you leave. How you have to do is the thing. So can I clear this? Once finish with definition, please let me know. Can I clear this one or not?
Noted, sir.
Good. Now we come back to this. So what is this Ampere circuital law? How to do that? That I am going to explain. Listen carefully. So the first thing is that you have a current flowing through a wire. Current I flows through the wire. Okay. So you know very well that the magnetic field, what is produced, it will be like a circle. Okay. So this circular path, the magnetic field is chosen. Is formed. Magnetic field is formed that forms circles. So it forms like a concentric circles. Okay. Now so at each circle, if the circle is the closer to this one, so the magnetic field is large. If it is going away and away from the coil, from the wire, it becomes smaller and smaller. You know that very well. Ideal sine theta by r square. So from that phenomenon itself, you know. So that from the Biot-Savart's law. Now the stuff is like this. See, we do something called Amperian loop. Amperian loop. Please understand this funda. Amperian loop, easy only. So you have a coil, not a coil. This is a straight conductor. First, later coil we'll think of. It's a straight conductor. Okay, now it's a straight conductor. So for the straight conductor, so some magnetic field you choose at any point, some magnetic field, you choose any point at a distance of P from the loop. Okay. From the point P, you describe a circle. You draw simply, what is an Ampere loop is nothing but draw a circle around the conductor, straight conductor. Okay, conductor. How you have to draw? Such that the conductor is perpendicular to the circle area to the area of circle you have drawn. Okay, you have drawn. So remember this. You draw the circle. So what is the circle area? This is what is circle area. And now you see the conductor. The conductor is exactly perpendicular to that. So what I mean to say is the conductor, I asked you to draw a circle. You draw a circle like this. There is no point. This should not be the way. You draw the circle so that it is the area of the circle is perpendicular to the conductor. The conductor should उसे घुसा के जाना है. Okay, it's like it has to pierce through the area. So such kind of thing. Imagine a cardboard. Imagine a circular cardboard. Through that the conductor is coming out. You have pierced the conductor out of the cardboard, circular cardboard. Now this circular cardboard, whatever I have chosen, is my Amperian loop. So Amperian loop tells you about the some magnetic field loop. Okay, magnetic field loop it is. It's actually magnetic field loop. Okay, it's not on the conductor. Okay, it is not on the conductor. It should not be on the conductor. It should be like the area of the your Amperian loop should be like, it should be perpendicular to the conductor. Remember that. This is the first part you have to know. Then we talk about something called element. Element is the next part. So once you return this, I will go through the next one. Is this clear? This part is clear. First part. Once finished, please let me know. And the other part is that what is the direction of the magnetic field at this point? It's given by the tangent. This is the direction of the magnetic field. So at any point on the Amperian loop, we want to find the direction of the magnetic field, draw a tangent. And this point is called the element dl. So the next point is that the dl, the element is chosen on the loop, on the Amperian loop. On the Amperian loop. On the Amperian loop. Okay. Not on the conductor, most important. When you are doing the Ampere circuital law, you have to choose the element on the Amperian loop, not on the conductor. Biot-Savart's law, it's on the conductor. Amperian loop, Ampere circuital law, you have to choose the element on the Amperian loop, not on the conductor. If you choose on the conductor, you are gone. This is a mistake, common mistake students will do. Is when textbooks, many textbooks are also not clear about this one. So the Amperian loop, there you have to choose the element dl. Okay, we'll do that once clear. Dl element is chosen on the Amperian loop, not on the conductor. Don't choose the Amperian loop on the conductor. The element is chosen on the conductor for the Biot-Savart's law, not for this, not for this one, not for this one. Okay. So once finished, please let me know. So once finished, please let me know. Finished, Amma? Hope you would have done it. Clear? Can I clear, everyone? So anyway, I will clear this off. Fine. Now the next part is that you have the conductor. So what you do is you will choose the element on the Amperian loop, and now the element direction and the magnetic field direction both are same for the subtle part. Now we will do the line integral b bar dot dl bar is equal to mu naught into I. Now the magnetic field is constant, both will have same direction, so the angle is 0 degrees. So you have integral b bar mod dl bar, right? Cos 0 is what we have, that is mu naught times I. And now the b bar is a constant, so b bar is out, so we'll write mod b bar out. And now integral dl. What is integral dl? That is the circumference, right? Circumference of the path code. What is circumference? Assume that this is at a distance of r from the center of the uh, r from the coil, so that is dl. So the integral dl is mu naught times I. Integral dl is nothing but the circumference of the Amperian loop. Okay, so that is d bar into 2 pi r, that is equal to mu naught I. You look at this one. This is the same expression for we got for the infinite conductor, that is mu naught I divided by 2 pi r. This is the same expression we got for the infinite conductor. Where did we see this one? So this is the conductor from which we took a finite conductor we have taken. We took this is the two situations. Anyway, you have the video record for that. Alpha, beta. You can see this one. Alpha, beta are the angles. Uh, what's the magnetic field? So that is given by mu naught by 4 pi into sine alpha mu naught by 4 pi r, sorry, mu naught by 4 pi r plus sine alpha plus sine beta. This is what the expression you have. And for setting, when you set mu naught I divided by 4 pi r into sine alpha plus sine beta. And when you set alpha is equal to beta is equal to 90 degrees, you are going to get this expression. For the infinite conductor, alpha beta is equal to 90. Why this alpha beta 90? See, this conductor, if it starts extending in both the ways, the angle alpha and angle beta are increasing. For infinite conductor, this becomes straight. Okay. So the angle goes to 90. So the reason you have this one. So for this reason, when you substitute alpha beta 90, you get this expression. This is for the infinite conductor. So this expression, the same expression we got from the Ampere's circuit law. This is for the infinite conductor, long, straight, infinite conductor. So this is the Ampere's circuit law. We derive the same expression, but in a different way. So the thing is, you got to consider the element on the Amperian loop, not on the conductor. Most important, not on the conductor. So once finished, please let me know. We'll solve one question and then we'll close the session today. So once finished, please let me know. Clear? Can I clear?
Yes, sir.
Okay, good. So fine. Okay, fine. Now the next one, we have a question. A straight wire is straight wire carries a current of 3 amperes. carries a current of 3 amps. Calculate the magnitude of the magnetic field at a point 15 centimeters away from the wire. So this is what we had to calculate. This is very simple. So the B is given by mu naught I divided by 2 pi r. That's the formula. So the value of mu naught is 4 pi into 10 to the power of minus 7. This is the value of mu naught. Mu naught is 4 pi into 10 to the power of minus 7. Remember this. And now I factor, I is 3 amps divided by 2 pi. And at what distance it is? 15 centimeters away. That is 15 into 10 to the power of minus 2 meters. So that's what the numbers you can plug in. And this goes 2 times. And anything else, 3 5 is 15. Okay, right? So 2 by 5, that is 0.4 into 10 to the power of minus 5 Tesla. So it's about 4 into 10 to the power of minus 6 Tesla. So that's the answer. So it's like 4 micro Tesla. So that's what the answer is. So with this we'll close today. So we will see the rest of the part on Wednesday. Next meeting will be on Wednesday. So I have some little bit of job also now. So rest of the thing will meet on Wednesday. Yeah, fine. Yeah, thank you all. So we'll meet on Wednesday. Bye. See you all.
Thank you, sir.
I'll upload this record
good
to you
night.
all. I'll upload this record to you all to today itself just now. Okay. So that you can have a view once again. Bye. See you. See you all.
Okay, sir. Good night.
Okay, right. Good night.